Hello, welcome to this final portion of session 13 on beams. In this portion, we're going to focus on the second moment of area or moment of inertia, which we introduced in the last portion. We're going to focus on being able to make calculations for these moments of area on a couple of standard shapes. So as a refresher, the second moment of area is equal to the integral of y squared dA, as seen here. So I is equal to integral of y squared dA. Now, one cross section that we will encounter quite frequently is one that looks like a rectangle. And if we think a little bit about what we've been doing for statics and pretty much our calculations up to today's session, with beams, we haven't been thinking about what the cross section looks like too much, right? We've been thinking, okay, draw the shear force and bending moment diagrams, and we leave it at that. But now that we're needing to calculate things like strain and stress, we do need to think about what the cross section looks like. And well, rectangular cross sections are pretty standard, and we'll do some more complex ones in the next few minutes as well. So if we're thinking about doing this integral of y squared dA, and we're saying that y is the distance from the neutral axis, okay, so here's y, here's the neutral axis that we've cut through the midpoint of the beam. This is the neutral surface, neutral axis, and also runs along the centroid, which we'll actually talk more about in the next session when we look at transverse shear. So we need a y squared, so well, there's y, so that's kind of straightforward, but we also need a dA. So what do we make as dA? Well, we can think of dA as kind of being what you see here, having some thickness dy and going across the whole span of this cross section. So that has width of b. And so dA can be thought of as, okay, what's the area of this little piece right here? Well, it's going to be b times dy. So dA is equal to b dy. We can then substitute the dA in to this equation and go from minus h over 2 to positive h over 2 to be able to perform this integral. So here it comes in kind of a number of steps. Integral of y squared b dy, okay, so b dy is the dA, going from minus h over 2 to h over 2. We perform the integration, and this is what we get. We get that's 1/3 b times h cubed over 8 plus h cubed over 8. This final form, I equals bh cubed over 12, is boxed for a reason, because this is, if not for the course, just as you're walking around in the street and you see a beam, you're like, oh yeah, that I for that beam, even though it's not an I-beam, is bh cubed over 12. And it helps us understand something about what gives a beam stiffness, okay, or what's going to help it be resistant to bending. We recall that the efficient engineer in one of the latest, one of the latest videos that is posted on the website talks about what happens if you take a beam and you have it kind of, well, let's put it this way. If you have a beam like this, right, where the thickness is very great and we put a load, say, right there, or if you have it kind of like this, right, where now you have a longer dimension in the B, all right? So look, I is kind of an indicator of how much it resists bending and how the bending stress will be inversely proportional to this quantity. So if I take a small b, all right, and have a big H, that would be this scenario. Okay, so H is big, B is, or this H is big and B is, pretty narrow, like this dimension here, then I can have quite a bit of resistance to bending. But if I simply turn this object like here, like so, and I have a lot of B in this direction, and my H is this, I'm not going to have nearly as much I, okay, because my long dimension is the B and it's not being cubed as it was here. So this quantity kind of allows you to think, oh, well, if I have a beam, right, and I need to think about how stiff it might be. Do I want to increase its thickness? Well, I'll get, the cube of that instead of if I just increase the width. I mean, if I increase width too, that helps. They both help, but the thickness is going to go, or the I is going to go with the thickness cubed. Another common cross-section that we will see for beams is one that is circular, okay? And so here we have the circle, and we're going to say that we can define some parameter w, okay, where w is essentially going from one side of the circle to the other. It's a chord. And, well, it's actually going from, it's half, right? So 2w would go from one side to the other, like this. So 2w. So we can do a similar thing where we think of the chunks, and we have 2w dy. Now, we are going to be wanting to integrate, okay, these different chunks, okay, and there are kind of different ways of approaching it, but one of them is to say, all right, I'm going to look at what is my w, right, and look at what my dy is, right? So similar, I mean, that's essentially what we have here, 2w dy, and this is getting, so this is getting the w in terms of z, the parameters that we have here, and c is the radius, okay? So z is going to be equal to the square root of c squared minus y squared. So here comes dA, this quantity here, and we can then look at integrating y squared dA, all right? And when we do that, we have a y squared, we have a 2 times this square root of r squared minus y squared dy. And when you do this all out, what you get is pi over 4 c to the 4th. Okay. Now, another way is to think of this system in polar coordinates. So we have r as the radius, okay? Theta is some angle, right, with this x, or it's actually the z-axis here. And we have our integral y squared dA. Well, what is y equal to? Well, y, okay, so in that direction is going to be r sine theta, like we see here. So now we can plug in r sine theta for y squared, but the dA is a little bit complicated, okay? And dA is going to be equal to r dr d theta, okay? And this comes from calculus, and also is going to be what we use in the integral. So I is equal to 0 to 2 pi, 0 to c, r squared sine squared theta, r dr d theta. Okay, that's the r squared sine squared theta, right? That's coming from the y squared. Um, okay, so now we can integrate this term, and if you use if you do the algebra out, okay, you can get the same quantity, I is equal to pi over 4 c to the fourth. All right, so these are two of the common cross sections that we'll encounter, and in a little bit we'll show how we can use the rectangular cross section or this formula for the rectangular cross section to come up with more or for come up with second moments of inertia for more complex geometries. Now, let's go back to an example that we've looked at previously in terms of bending moments and shear forces and strains as well. Here we have a cantilever beam, length L, with a force F. I think we used P earlier in the session. And now we're prescribing a profile or a cross section that this beam would have, right? So we're extruding essentially this cross section out. Question is, where's bending stress the highest and what is its magnitude? So what do we do? Well, let's go ahead and go through the exercise again of first calculating out what the bending moment looks like across this beam. And to do that, we would first perform external equilibrium, whether you use equilibrium or you use integrals, okay, to graph this profile, we need to start with external equilibrium. So once again, we draw our diagram and we look at what the reaction force R is, and we look at what the bending moment at the right side or at this left side, but it's MR because its reaction might be. And we get the following. Now let's look at the boundary conditions at the left side. So in this case, if we were to take a thin slice and were to use our nomenclature that we have here, we can say that the moment on the left side is equal to minus FL. If we look at the boundary condition at the right, we can say that M is equal to 0. Now, we can kind of skip a few steps because we have a little bit of experience. One thought is, well, there's no distributed force, so that means that the shear is going to be a constant, and we integrate that up. That means that the bending moment is going to be a line with some slope, okay, given by the constant shear. So we have the boundary conditions. We know it's supposed to be a line, and so we go from minus FL to 0. The bending stress is given by sigma equals negative my over I. And we know that these bending stresses are going to be maximums at the top surface, the bottom surface, okay, up here or here, right? So what is that? That's y equals h over 2, right, half the thickness from the neutral axis. And now we want to figure out where along the beam we're going to have the maximum moment, right? So we've got a c is equal to h over 2, or, we're plugging c into y, all right? We have this I, which is bh cubed over 12, and the max is going to be, well, where we have a maximum bending moment, or, a minimum, whatever, but we look at the absolute value here. So we plug in this moment minus FL, and we plug in our h over 2, we plug in our I, and this is what we get. Okay, so that's going to be the magnitude of the maximum bending stress, and that would be, well, either here or here, on the top or on the bottom. On the top, that is the quantity we have. It's positive, it's in stress, right? This is or tensile stress. It's in tension, right? So it's kind of being bending this way. And on the bottom, the quantity, the magnitude is the same, but it's negative and it's in compression, right? So you could say, oh, there are two locations. At the top, it's in tension. The bottom, it's in compression. Okay, let's now go back and discuss the parallel or discuss moments of inertia in more detail. I mean, really, I guess I should say these are really moments of area, okay, or second moment of area. All right, so let's just, because there is a little bit of a difference here. There's not a mass, and we use polar moment of inertia when we're dealing with resistance to spinning about an axis. We do use the term moment of area or second moment of area here when we're dealing with beams. So we've derived this already, and I want to be able to use it. I want to be able to composite. Like, I would like to be able to kind of think about systems where I have maybe multiple rectangular cross sections and composite them. Or some people might say decompose that system into a set of rectangular beams. And we could always go back to the integral of y squared dA, but that could get tedious and complicated. So we can use the parallel axis theorem. Now, you may recall using this previously in some of your physics classes. And a lot of times when we do it like with the polar moment of inertia, okay, we're thinking about a polar moment of inertia, okay, often, and we're thinking of some type of moment of inertia with a mass, and we say it's going to be mL squared or md squared. Since these are areas, okay, we're thinking of second moment of area plus area times distance squared, okay? And what's also interesting about this form of the equation is that there's a summation. So these moments of area can add, they can sum, okay? And if, for example, you have this rectangle and you have another rectangle and they're sharing the same neutral axis, then D is 0, okay? So you could sometimes, if you were to like put multiple, increase the width, for example, the beam, okay, of this cross section, that's kind of like saying, hey, I have one eye, another eye, and I can put them together, okay? They're on the same, they have the same neutral axis. The centroid of that object is in line with the neutral axis that we already have. The centroids are aligned, so we don't have to use any distance. But if we go away, okay, from up or down, if we go away from this neutral axis, if the centroid of this new rectangle is away from the neutral axis that we're prescribing, that's when we need to take into account this D and this D squared term, okay? This will, I think, become a little more obvious as we do some examples here. Okay, so I-beam. This is what it looks like. And I-beams are great because they allow us to get high moment of inertias with little mass or a smaller amount of mass, right? So this top portion and this bottom portion, they can take a lot of the stresses, the bending stresses, and we don't have to use all the mass that we have if we have a rectangular cross section. So we get rigidity, strength, if you will, from this I-beam without all the mass, which is why we use them, okay? Because, well, mass is mass, which so makes things heavier, which is usually not what we're going for when trying to build structures higher and higher and higher. And mass is also cost. Okay, so we're trying to make these beams of lower cost, so we want to use less material. But how do we calculate what the second moment of area is for this shape? Well, let's first start with what seems pretty basic. There is a rectangular section in the middle, right? Just like that. And that has some height 2a and some width c. Now, that's great, but I have the top and the bottom, right? I have this section here and I have this section here. So we need to somehow do some type of summation, right? And figure out what the contributions to the second moment area might be for these horizontal pieces. So we can go ahead and kind of draw them there. And when we look and see that the centroid, okay, of these rectangles is a distance of A plus, sorry, I didn't mean to, A plus this half, or half of this B. Okay, so that's what you see here. It goes up to this. This has a width F, okay, that we see here. And so what we can kind of get a feel for is that this F is a new B, a width, right, for the B h cubed over 12. And this B is actually the H. Okay, so now we have an FB cubed over 12, okay, over here, and we have one actually down here too. So we're going to have double. And the centroid is off, as we discussed previously, right? So we need to know the area of this. Well, the area of this is just BF, and the distance, as we discussed previously, is A plus B over 2. So what does the math come out to look like? Okay, it's a little bit messy, but let's talk through things. So this is essentially the BH cubed over 12 for this section, right? The height now is 2a here. So we put that in for h, and we get 2a cubed, and c is the width. So this term is pretty straightforward. This 2 means that we have one above and one below. Okay, so we're going to double. That's a nice thing, right? We can sum. Now, and it's symmetric about this neutral axis. FB cubed over 12, we discussed that, right? This is the width now. This is the height. And so we can plug that into this formula, and we get that FB cubed over 12. But it's further off than the neutral axis, the centroid is, okay? And so we said, okay, well, we need the area of these, but that's BF, and we need the distance to the centroid, and that's going to be some d squared. And we just said that, well, that d is actually the A plus B over 2. All right? So we now have another tool in our box for being able to look at the decomposition or composition of complex shapes using simpler ones like a rectangle that we've discussed previously, going straight to the integral of y squared dA for the second moment of area. Let's look at another example. So here we have a beam that is having a moment applied to the end, okay? And yes, we have a wall here, but if we ignore gravity, there's going to, we ignore gravity, there's not going to be a reaction force. There's just going to be a reaction moment here. And so this is essentially a beam that is experiencing a constant moment across it. And you could do that quickly with equilibrium if you want, okay? We use an I-beam for our cross section, and we'll say it has B with B has total height h, and now we're going to describe this W as a web thickness for the profile. We ask ourselves the same question: what is the maximum bending stress? Well, a couple of things here. One, we know that the bending stress will be at the top or bottom of this beam, and it will be where the internal bending moment would be a maximum. But like we just discussed, the bending moment is actually constant along this entire beam, the way this load is applied. So that is just going to be m. The equation we have is sigma is equal to negative my over I. And, that negative is interesting. Sometimes I look at the beam and I just say, oh, I think, if I'm applying the moments here, the top is going to be compression, the bottom is going to be in tension, but it's nice to know that that negative does work out with the convention we've selected, we've chosen. The sigma max is going to be greatest at either the top or the bottom, as we discussed previously. So now we get to calculate the I. So how do we go about doing that? Well, we can approach it this way, okay, where we have now a decomposition, okay? So this is B, this is H, and we're going to call this Q, all right? And we're going to call this D. Now, am I doing this correctly? All right. Can you get away with this? Ask yourself that question. You're like, wait, but these are off-centered. This is off-centered from here, okay? But notice, the centroids of all these objects still lie on the neutral axis. Like if I were to draw a neutral axis, right, or a neutral axis right through here, the centroids are all still there. So I'm using the summation or now the subtraction property of the parallel axis theorem, but I don't have to account for that di squared term and that area term, okay? So this approach is fine. It's correct, all right? I'm removing this material, and I am removing that second moment of area from it. And we can be a little more detailed in describing what D is in terms of the parameters that we're given, and also what Q is in terms of the parameters that we're given, and then we can write out the final solution for what sigma max is. Okay. Let's look at another cross-sectional profile. And I have said before, you have to be very careful about whether the centroid is on the neutral axis or not. Let's look at decomposing this plus sign, okay? And we have geometry, right? The whole thing has height h, the whole thing has width b, and we'll say that the web thickness or these sections have this thickness w. So maybe I can look at this and I say, okay, BH, and I do my subtraction again, right? I just did subtraction, it was very convenient. And we'll define these chunks, all right, with D and Q. So then I'll just write out I equals BH cubed over 12, right? That's this one, minus like nice 4 of these things, and D cubed over 12. And I could say that this 2D plus W is equal to B, right? And we could that's D plus W plus D is equal to B, right? And I could simplify this further, and you can look at 2Q plus W is equal to H and solve this as well. But then it looks good, but what I do wrong? We did this analysis thinking that, well, we're not accounting for the fact that the centroids for all 4 of these are off. So this could be fine. We would just have to subtract the distance to each of these from the neutral axis, the vertical distance from each of these. So, times 4 and figure it out. I didn't do that, so this analysis is incorrect. And like we're saying, we would have to appropriately use the parallel axis theorem on the 4 regions to account for the fact that they're off from the neutral axis. It's not that hard. It's a little bit painful because it's like, a W over 2 plus a Q over 2, and then I had to figure out what the area is. So it's not so bad, but I didn't do it, so it's incorrect. I think an easier way, potentially, to solve this cross-section or figure out the second moment area for this cross-section is to go ahead and take our horizontal portion, keep it there, keep the vertical portion there, okay? And they're now both having their centroids on the neutral axis, but I have double counted this center piece, right? I have material here and I have material here. So I can create one final element in the middle that we subtract away, okay? And once again, all of these are on the central axis or on the neutral axis. Their centroids are all on the neutral axis. So we don't have to use that other portion, the AD squared portion of the parallel axis theorem. We can just add and subtract these different quantities. So we have BH over cubed essentially for the first 2. Okay, I mean, I always just say BH cubed over 12 in my, oh, did I say over 2? BH cubed over 12 in my head, right? But we got to make sure we know what B is, and we've got to make sure what H is. And then this is a square, right, is BH cubed over 12 with the sides equal to each other. So that's W to the 4th over 12. So that's also, one that comes up not too infrequently. And we can write out the final answer as we see here, okay? So hopefully this portion of the session has gone through different ways of looking at the second moment of area. It's a little bit more mathy, and it's actually kind of fun, to decompose or compose these different geometries and then calculate the I using the parallel axis theorem. And that's just one component to being able to then solve for the bending stresses across the beam. For the last question in this session, we have a beam, an overhanging beam. So this is an opportunity to do another example of interesting geometry that I don't think we've really assigned up to this point. So take a look at how you would, create the bending moment and shear force diagrams for this system. And then another thing that's maybe a little bit different is we're saying we're not going to do our query at the top surface or at the neutral axis. It's just 0. We're going to do it at some location here. Okay, it's not super common because usually you're concerned about what the maximum stress is, so you're going to go to the outskirts. But we're attempting to say that, look, we can do this at a given location wherever we want in the beam. What is this? We can calculate the bending stress wherever we want in a beam with a pretty standard cross section. One thing to keep in mind when you look at exam 2 from 2015 is the definitions of how we calculated out the bending moments across the beam and what we use as coordinate systems. Okay, so in that case, I did not take a cut and cover the left. Okay, I did not go from the right. I went completely, at least in the solutions, I went completely from the left. All right, And so be careful with that. You'll see that there's kind of this x term here, and then there's like an x prime term that I defined starting from this roller. So the question is a little bit tricky, but it's saying a distance of d from the right end of the beam. All right, so we're going to need to do a little bit of subtraction to be able to get this appropriate location in our bending moment equation. Well, what have we learned in this session? Not in this portion, but in this session. We've covered how we can relate the radius of curvature of a beam to local strain, and we've looked at tensile and compressive strains. We've also discussed how we can relate the internal moment, bending moment, to normal or bending stresses within a beam, as shown here, right? And now when we look at, oh, where is it? It's still not coming. There it is. And when we look, a little bit more carefully here, right? Now this diagram probably makes a little more sense. You see, oh, there is a bending moment applied, okay, here, or this is an internal bending moment, which causes there to be a compressive stress above the neutral axis and a tensile stress below the neutral axis. Okay, thank you for joining this session, and I hope that it is helpful. And if you have questions, please feel free to let me know. Have a good one. Bye-bye.